In this video, we're going to talk about rotational kinetic energy. This is the energy associated with something spinning around. We know that we have translational kinetic energy from our study of motion and energy. This is the energy of something moving, but it was something moving in a straight line. So we solved problems with something like a ball that was traveling in a straight line. If I throw this ball with a certain speed and it flies through the air, we would use this to calculate the kinetic energy. But now we can also talk about, well, there has to be energy associated with something rolling, or spinning, I should say, rotating, because I am doing work on this object to get it to spin. So we're going to make our usual changes, right? Velocity is going to turn into angular velocity. Let's zoom in on that a little bit. And mass is going to be replaced with the moment of inertia. And I have this relationship, 1/2 times the moment of inertia times the angular velocity squared. That's the energy of something that is rotating. It's moment of inertia times the angular velocity squared. Now, this means then that an object can have both kinds of kinetic energy, can't it? Because I could have the center of mass moving, and it could be spinning at the same time. So not only could I picture something like, a curveball flying through the air that is rotating as well as it's moving, from left to right, but it's also spinning. But this has also got to be true of things that are rolling, doesn't it? Because I am moving my center of mass here in this case from right to left, but I am also rotating about my center of mass. So I have my moment of inertia times my angular velocity squared, my rotational kinetic energy, plus 1/2 mv squared for the object's center of mass moving linearly. Let's consider a sphere rolling down an incline, and we're going to see how taking into account the rolling of the object changes its motion. Everything we've had on an incline up to now has slid down. So if this were the sphere, everything we've had moves like this. That's the only stuff we've analyzed. We had blocks and things like that that slid down a sphere. Now we're going to let this thing roll down the sphere. That's how we're going to picture this problem. Before we work a lot of the algebra, let's say that we want to find a statement for the total energy of this object at a certain height, h, above, or a certain position, we'll say y, above the ground. So here's my sphere, I know that the total energy, that's got to be the k for, we'll say, the translational kinetic energy, plus the k for the rotational kinetic energy. So I have k trans plus k rotational, plus we'll have a gravitational term, Pe sub g, the gravitational potential energy. That's going to then look like, well, my translational kinetic energy, that's 1/2 times mass times the velocity of my center of mass squared, plus 1/2 times I about my center of mass times my angular velocity squared plus mgy. So that's going to be the statement for the total energy of this sphere as it's rolling down at any height y. It will have a certain speed, and this will allow me to track my total energy. So let's use this to find the speed at the bottom of the ramp, and then we can do a quick comparison to the total speed that we would get if I just slid down the ramp. So we'll do energy conservation. It starts the same way that energy conservation started a few chapters ago. Let's say the energy at the top has got to equal the energy at the bottom. At the top, I know that I have 0 kinetic energy, both translational and rotational, but I do have gravitational potential energy. So I have the mass of my object times g times h was the height of my center of mass at the top. And then at the bottom, I'm going to have two kinds of kinetic energy, 1/2 mv squared plus 1/2 I omega squared plus 0 for my gravitational potential energy. So again, I am thinking about this formula here for both the top and the bottom, where my center of mass has moved through a height h, and at the top I am starting from rest and letting go, so these two terms are 0, and I only have this term surviving. And at the bottom, my height is 0, so this term goes away, and only these two terms survive. Now, the things that we're going to use to make this equation so that we can find the total speed of the sphere, that's what we're looking for, we're going to make some substitutions. We're going to say, okay, for a sphere rotating about its center of mass, we have 2/5 mr squared. We got that from that chart like we had in class last night as the time of making this video. And we are going to apply the condition that we are rolling without slipping. Remember that when we roll without slipping, we can say that the velocity of a point on the edge is equal to r times omega, or rather the velocity of the center of mass is equal to r times omega for that slipping object. So this allows me to substitute. We'll see that omega is, let me make a cleaner version of that. There we go. Omega is going to be v over r. So we're going to put this into this formula and let's see what we get. So I'm left with, okay, this side had mgh. Whoops, that was a capital H, just what I've chosen for this problem. Equals 1/2. These first two terms don't change. 1/2 mv squared plus 1/2, and then our moment of inertia, 2/5 mr squared. And then our omega, we said, was v over r squared. So now I have relationships that only have v and all my other given parameters, h and r, etc. So if we work with this a little bit, right, this is going to be v squared. My r squareds are going to cancel. And I can do some algebra. I'll leave this up to you. I'm going to do the infamous ... And there's not quite a bit. There's a little bit of algebra. I think it would be great practice for you to make sure that you can also get an equation for v. Right? Now is your chance to pause the video and see if you can get an expression for v just in terms of g and h. And what you should get when you do that is 10/7 g times h. Now on its own, this might not mean much. You say, okay, fine. Here we have this velocity that we solve for. Let's quickly do the case where my sphere just slides down. So if the sphere just slides, it doesn't roll. Well, this is the question that you dream about being on the test, because this is going to be easy, right? mgh at the top equals 1/2 mv squared. We can find the velocity then to be radical 2 gh. So we see that the speed that we got, whoops, pardon me. We see that the speed that we got, I didn't mean to do that, and now it's doing exactly what I'm telling it to do. Choose a page, done. Fine. The speed that we got here is slower than if it were to just slide down. Well, this should make some sense, because if we look back at that very first statement, the energy that we had at the top has to be shared, doesn't it, between translational energy and rotational energy. So my translational speed has got to be less because I'm giving some of that initial energy to my rotation as well. So as my moment of inertia changes, that consumes more of the energy, or it needs to share more of the energy that we had initially. So we get a slower speed than we got if we just considered I thought I wrote this, maybe I undid it. What we get when we just slide down due to the rotation taking some of that energy.